All right. Gonna give it a minute here before I start going over stuff. Just to give people an opportunity. I said I'd start at 7:30, and it's 7:27 right now. So in about 3 minutes, I'll start going over things. Um, but what I'm gonna start with is the extra practice question that I put underneath the opener today. You will see a question like this with an incline and a pulley. So know how to draw the free body diagrams of these objects, know how to write equations to describe the forces and their accelerations. So that's going to be the first thing that we're going to cover today. And basically, I'm just going to look at the test. So I have the test up in Mastery Manager on my second monitor. You guys can't see it, obviously. And I'm just going to look through some of those questions, and I'm going to try to hit on some of the ones that I think are probably going to give people some difficulty, and just make sure that we know how to do some of the basic problem solving steps to solve these questions. Going on. And once again, if you guys have a Twitch account, you could ask questions in the chat. If not, what I'll do is I'll have Remind. I got Remind on my phone, and I'll just be answering questions on there. But hopefully you guys find this helpful. If it is something that you guys think is useful, then I would be happy to do more of it. I mean, I stream for fun anyways, so I don't mind hopping on to answer questions or go over things. So physics, yeah, we're doing some physics work. Fun stuff. So like I said, I'm gonna wait like 3 more minutes for people to filter in, for the view count to go up a little bit, and then we'll go through some of those questions. But what I really wanted to start with was this incline and a pulley question. No biology, just physics here. Physics. We'll give it a minute, and then I'll start reviewing some of these. And like I said, I'm just gonna go through the main questions that I think are going to be kind of the more difficult questions on the test, and maybe just some of the concepts we haven't gone over or reviewed in a while. So hopefully it's useful. Hopefully it's helpful. But if you guys have your laptops, which I hope you do, if not, if you're watching on your phone, whatever, that's fine. But if you have your laptops, you might want to refer back to this question once we're done. Disagree, Phoenix. Actually, I would prefer those be separate worlds. I'd prefer those be separate worlds, but that's okay. All right, so let's get started with this incline. I only have one account. I'm too lazy to create a new account just for educational stuff, but is what it is. All right, so let's start with that incline with an object, 2 objects. So it's a system of objects problem. So we have an object on the incline, and then we have an object hanging below that's on a pulley. All the money is actually donated to the robotics team. So I am not making anything. I would feel too weird. About that. Taking money from people. No, I donate all my money. Donate it to the robotics team. All right, so we have these 2 masses connected via a rope over a pulley. And basically, they described this as object M1. Let's refer back. And object M2. So this is M1 here. And this is object M2 right here. And once again, I hope you guys are taking notes. Take notes. So first thing we're going to do is draw some free body diagrams. You gotta not take shortcuts with this. You really have to take the time to draw out the free body diagrams of all the objects being described in your system, especially for problems that are like this. Okay, so let's start with the M1 object. So that's basically an object on an incline. I'll keep the color scheme going here. So M1 is an object on an incline, and I feel like it helps for me to like draw the incline with the free body diagram just to make sure that I'm like getting the proportions and everything right. And once again, if you guys have questions, you could message me a reminder. If you have a Twitch account, you could ask in Twitch. And then we have, obviously, the force of gravity we always have pulling down. Now, what you guys have to kind of think is synonymous with the force of gravity is m times g, the mass times the acceleration due to gravity. So the force of gravity, or the weight of the object, can always be found by taking the mass of the object in whatever kilogram amount it is and multiplying it by the acceleration due to gravity, which we remember, or should remember, is 10 meters per second squared. We also have a normal force, which is going to occur perpendicular to the surface. We'll label that F sub n for normal force. That's the force provided by the surface onto the object. In this case, we also have a tension force pulling back to the right of this object. Now, this specific question said that the ramp was frictionless, right? So it says, ignore the friction force, blah, 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 moment of inertia. You don't need to know any of that. Okay. So we got that. Now, we also know this angle here. I have so many different colored pens. It's ridiculous. We also know this angle over here. And if we know that angle, then we can break up the weight into two parts, the perpendicular and the parallel parts. Let me use different colors for this. I have so many colors. All right. Let's get a good color. Let's get pink. So we'll do pink as the perpendicular. And that should be equal in size to the normal force. I think I bought a pack of like 15 different gel pens. I love my gel pens. The normal force should be equal in size to the perpendicular component of gravity. So I'll call that Fg, and I'll mark it with that little upside down T to mean perpendicular. I know, that's what nerdy science teachers do. We brag about pens. And we have Fg parallel. Okay, now I'm drawing it down here, okay? But really, what it's doing is it's pulling the box down the incline this way. Okay, I mean, that's really what's happening here. So this blue line here, we'll call that Fg parallel. And I'm going to draw two parallel lines to indicate that. Now, if our angle is here, which is how that works when you have an object on an incline, the angle that the force of gravity components are at are the same as the angle of the ramp. And I mean, you could prove that to yourself with like a geometry proof. So if we know the angle here, well, then we have a right triangle, okay? This pink line, I know is the adjacent side, because it's touching the angle. I'm sorry, it's touching the side of the triangle. The side of the triad is touching the angle, but it's not the hypotenuse. So if you have a side of the triangle that's touching the angle, but is not the hypotenuse, that's the adjacent side. And we can find that by doing the hypotenuse, which is mg, right, the weight, times cosine of our angle, okay? Now, what we also know is the normal force must be equal to that force, because this object is not accelerating up off the ramp, it's not accelerating down into the ramp. So those two forces must be equal. Oh my God. F's in the chat, come on now. So that normal force is also going to be equal to mg cos theta. It has to be, because this object is not accelerating up or down at all. Now, the parallel component of gravity is actually the opposite side in this example, because it is facing the angle. So Fg parallel, we're going to find by doing mg sine theta. F equals ma is a better one. Thank you, Pope Derps. Pope Derps, hold on. Pope Derps is a friend of mine. Hold on. Just so you have that power. All right, F equals ma. We know that. So we got basically all the different forces acting on this object. We have the normal force, we have the perpendicular part of gravity, we have the parallel component of gravity, and we have tension. We don't really know what tension is yet, but we'll get there. Okay, now for the second object, and this was M1 that we started off with. I haven't even gotten to the second object yet. Let's do that. Yeah, let's actually try to learn, guys. Let's actually try to learn. So the second object, M2, has two major forces acting on it, okay? it has the weight. Okay, now notice its weight is technically going to be different than M1's weight. And what I should have done, but I didn't, was I should have labeled this instead of mg, since that's M sub 1. I should have labeled all these M sub 1g. Because a big mistake you can make while doing these problems is confuse the two weight forces. I mean, they're both found by doing M times g, but the masses are different. The gravities are the same, but the masses are different, so you have to be careful with that. Also, let me know if like the focus or the sound quality is okay. So the weight of the second box can be found by doing M sub 2g. Once again, the little 2 and the little 1 are just for labeling, just so we can keep these two objects separate from one another. Now, what's opposing that weight is the tension force. Okay, now notice, that tension force going upwards for this object has to be the same as the tension force going to the right of this object. Okay? These, because it's the same rope, right? It's the same rope. Those two tensions have to be the same. The next thing we probably want to do is get a net force equation for each of these two boxes. Okay? Get a net force equation for each of these two boxes. Now, for the second object, the net force is pretty straightforward. It's just these two forces. And since they're going in opposite directions, we're going to subtract them. I actually should have drawn this. I drew this a little inaccurately. I should have drawn this tension force a little bit larger than the force of gravity because this object is accelerating upwards, I believe. So technically this isn't correct. These should not be the same size. This should be bigger, but whatever. Doesn't matter too much. So the net force of the M2 object is just the mass of the object multiplied by its acceleration, and that's equal to the sum of the forces. So if M times A equals the sum of the forces, well, we can write that all out. So M2A, the mass of the second object times its acceleration, is equal to the sum of these forces. Now we have to think. The first thing you should ask yourself is, which of these two forces is going to cause this object to move? Okay? It's going to be the tension force in this example, because the problem says, and let's refer back to that real quick. I have so many pens on my desk. The problem says, and it even has a little arrow there to show you that M1 block is going down the incline, the M2 bucket is going up the incline. So we know that the tension force is the greater force here because this object is going to be traveling upwards. So M2A, we're going to list the force that causes that motion first, tension. And since these are in opposite directions, we're going to subtract these two forces, okay, in order to get the sum of the forces. So minus the weight pulling down, and that's M sub 2g. So the mass of the second object times the acceleration due to gravity. All right, so that's the net force on this first box. Okay. Now the net force acting on, the second box. The net force acting on the first box, a little bit more complicated, but we could still do it. Now, what we're going to notice here is that the normal force and the perpendicular force of gravity are going to cancel out. Okay? They have to. Because once again, that object is not accelerating. So the only two forces causing a acceleration of this M1 box is the tension force and the parallel part of gravity, the mg sine theta. So let's draw that M1 box real quick. Okay, once again, the only major forces we're concerned about here are the tension going up and the parallel part of gravity going down. So the net force equation for this first box, once again, mass times acceleration, and that is the acceleration of this whole system as it falls, is got to be equal to, now once again I have to think, which of these two forces is causing the object to move? Well, if the object's going down the incline, it's got to be the parallel component of gravity. And once again, I know that the parallel component of gravity is equal to m1g times sine theta. So I'm going to write it as that, as what it's equal to. So m1g sine theta minus the tension force. Okay. So now that I got these two equations, what I could do is I could solve for the acceleration of these two boxes. Sponsored by Nike, I wish. I wish. I can solve for the acceleration of these two boxes. All right, I can at least put the equations in terms where I can find the acceleration of these two boxes. Okay. Now, what I can do is I could just combine these two equations. So m2a plus m1a, and let's do this in a different color. Let's do this in black. So m1a plus m2a. So let's actually write it like this. m1 plus m2a. All right, same thing. I'm just combining the left side terms together. Equals, all right, now I have to think here. These two tension forces are going to cancel out because it's the same tension force pulling back on this box as it is pulling up on that box. And since I'm subtracting tension over here and tension's positive over here, they're going to cancel. So I don't have to worry about tension. I'm just going to write what's left. The mass of the first box times the acceleration due to gravity times sine of theta minus m2g. And then if I wanted to solve for acceleration, Solar, you're about to be muted, by the way. My handwriting is art. It's so trash. And then if I wanted to solve for acceleration, all I have to do is divide both sides by the m1 plus m2. Okay? So the acceleration of this box can be found by taking m1 times the acceleration due to gravity times sine theta minus the mass of the second box times the acceleration due to gravity, and I can divide that whole thing by m1 plus m2. So kind of a long roundabout problem, but that's how you would find the acceleration of that box. Okay. If you needed to rearrange to solve for something different, well, then it's just algebra from here. Okay. You could also, if you wanted to solve for tension, this would be actually a very difficult thing to do without any numbers. You can then plug this acceleration equation back into one of these two equations and then put it in terms of t. That's a little bit more complicated. My cat is attacking my feet. Quit. It's a little bit more complicated of a problem. Okay. But once again, know how to draw the free body diagrams of these objects. Okay, the object on the incline, if there's no friction, had tension, the normal force, and gravity, which could be broken up into the perpendicular part using cosine, since the angle's right here, that's the adjacent side, and the parallel part of gravity, that would be going down the incline, and that's going to be found using sine. For the second object, it's just hanging. All we have is two things, the tension force and the weight, which is just m2g. Okay. That's all it is for that problem. Then what you want to do, write your net force equations. The net force is always equal to ma, just whatever the acceleration of the system is, and that's equal to the sum of the forces acting on that object. The forces causing the object to move are positive. The forces resisting the motion are going to be subtracted. Okay? Let's do an Atwood machine problem because that's something that's probably going to pop up. Stash is selling robotics merch in the chat right now, which I wholeheartedly support, by the way. Get yourself some cyborg swag. Yeah, I gotta take a drink here. My throat is parched. All right, throat is parched. All right, let's do an Atwood machine problem. Now, you could use the shortcut on the Atwood machine problems. I'll probably show it both ways. Am I going to stream chemistry too? Hey, wait, I think I know who that is. Sam. I thought you were banned. Sam. All right, so we're going to have two objects here. Let's make up some. I'm going to just make up these numbers here. So let's have an object with a mass of 35 kilograms. I don't know. And then a object with a mass of something bigger. Let's say 120 kilograms. We might, Molo. We might. Stay ready. Stay vigilant. Thank you for my mods in chat, by the way. My mods are all former, like, graduated robotics students. So kids that used to be in robotics but are now adults who are off doing bigger and better things. Okay, so once again, let's start off by drawing free body diagrams for these two objects. Let's start with the 120 kilogram mass. So there's two forces acting on this object. When we draw this out, there's the tension going up, and there's the weight going down. Notice the weight's going to be bigger than the tension force here. The weight's going to be bigger than the tension force because this object is going to be accelerating downwards. So the weight, force of gravity, we could find by doing the mass of this object times the acceleration due to gravity. We could do that right now. We know the mass is 120 kilograms. Let me write it out. And we know the acceleration due to gravity is 10 meters per second squared. So the force of gravity, or the weight, 1,200 newtons. Okay, so I know this force value already. It's 1,200 newtons. Okay. Same with this object. It's the same thing. Anytime you have an object hanging from some sort of string or some sort of tension force, the only two forces you're going to have if you're on Earth is the tension force and the weight. I mean, what else is there? So once again, for this one, you have the tension force going up and you have the weight going down. Now notice for this object is going to be traveling up, right? Because it's going to be pulled upwards. This object's going to be traveling down, right? Because it's the heavier mass. So once again, we have a tension and we have a weight of this object. So that's the force of gravity, and that's equal to mass times the acceleration due to gravity. Once again, I could do this right now. My mass is 35. My acceleration due to gravity is 10. 35 times 10, that's 350 newtons. Now what we can do, if we're going to do it the long way, which it seems like we're going to do that right now. I disagree, Skylar. You got to earn it. Is we could write our net force equations now. Now our net force equation, remember, is just your mass times acceleration is equal to the sum of forces. And this is the equation I'm going to use for almost all of these problems. Okay, almost every single one. If anything, you guys should give me an A because I'm taking my home personal lifetime to help you guys get through this test here. It's because I care. You know, because I care. So anyways, I'm being a loser, don't mind me. So the mass times the acceleration, so 35 kilograms times the acceleration here is going to be equal to the sum of the forces. Now the tension force here is going to be greater. I'm going to do T minus, and then I have the weight pulling down. So that's going to be the smaller one. So T minus 350 newtons. Now for this other object, it's the same deal. The mass times acceleration is the sum of the forces. Well, the mass is 120 kilograms times the acceleration. Same acceleration, by the way, because they're tied together, is equal to the weight, 1,200 newtons, minus the tension force. Now, I put the weight here first because that's the one causing the motion, right? The weight here is the force that's going to cause the acceleration downwards. The tension is just going to oppose that force. So if we're going the long way, what I can do now is I can combine these two equations. 35 plus 120 is 155 kilograms. A is still A. The T's are going to cancel out, right? I got a T there, T there. They're going to cancel. And then it's just 1,200 minus 350. And I'm sad to say I do need a calculator for that. What is that? 850? Is that 850? I mean, I think it's 850. Let me check. It is 850. Look at me. Didn't even need a calculator. 850 newtons. Okay, once again, the tensions are going to cancel out because you're adding and subtracting by tension. Now to get the acceleration by itself, well, in order to get the acceleration by itself, just divide both sides by 155. So the acceleration of this system is going to be equal to the force, 850 newtons, divided by 155 kilograms. So 850 divided by... That I do need a calculator for. I get an acceleration of 5.5 meters per second squared. All right, now if the question asks me for tension, 850, yeah. They're roasting me for not knowing that. I figured it out eventually. Now, if you're going to solve for tension, what we can do is we can just come back up to one of these two equations and just plug in for A, right? We already know an equation solving for tension. I'm sorry, I got the cross out mark through the T, so let me rewrite this. We already know that the mass times the acceleration of this object is equal to the tension minus 350 newtons. I now know the acceleration. It's 5.5. So I can do 35 kilograms times 5.5 meters per second squared is equal to T minus 350 newtons. And then I can just add 350 to both sides. And I get the tension is equal to 35 kilograms times 5.5 meters per second squared plus 350 newtons. Once again, I need a calculator for that. Do that one in your head, Han Molo. Yeah, I didn't think so. And we get the tension force here is 542.5 newtons. You missed Atwood machines? Red. Oh, Red, you're funny, dude. All right, so we got the tension. Now, I could also do that the shortcut way, the way I showed today, okay? So the shortcut way, now you missed knowledge is what you missed. The shortcut way is just the acceleration of the system is equal to the net forces acting on the system. Well, we know of two net forces. The weight pulling down here, the weight pulling up there. So that's just the 1,200 newtons minus the 350 newtons. And that's divided by the sum of the masses. 120 plus 35 is 155. So that's a shorter way to get the acceleration. It's just knowing it's the sum of the outside forces divided by the total mass of the system. And that would also just more quickly get me that 5.5 meters per second squared. I can then plug that in just knowing the net force of one of the objects. I could plug in the acceleration, just like how we did. I'm running out of space on my desk. Just like how we did down here to get that tension force again. Okay. Yeah, Red CSGO is a college physics student who still asks me for help. So he's been through it before. Okay, let me look through the tests real quick, and let's find another question that I think you guys struggle with. All right. There's another one that we can do that we went through the opener today with, and it's similar. Okay, you got some boxes. Either they're connected like by a rope, or they're connected by like pushing on each other, or whatever. Okay, so let's say we have two boxes, or let's say three boxes. We got 2 kilograms. We got a 4 kilogram box, and we got a 3 kilogram box. Okay, now let's say we have these boxes, they're being pulled by a rope. So there's some sort of applied force here. And let's say the surface is icy, so there's no friction. Okay, and we want to know what the force on a specific one of these boxes would be. Okay, so let's say I'm worried about the 2 kilogram box. I want to know if these objects are all, I don't know, connected together with string, or I don't care, whatever. Okay, if they're connected together somehow, what amount of force is causing that 2 kilogram object to accelerate? Now, once again, we could use kind of that shortcut we talked about today. Now, if there's no friction, the only outside force acting is the applied force. Okay, and once again, I know the acceleration of the system is equal to the net outside forces divided by the total mass. Well, the total mass here is 2 plus 4 plus 3, and I don't need a calculator for that one to know that it's 9 kilograms. So the acceleration of the system is the applied force divided by 9 kilograms. Okay, now if I want to know how much force was acting on this one specific object over here, well, then I'd have to do an F equals ma. Okay. Cats are better than dogs. Hold on, we need a cat break real quick. Cats are better than dogs. Okay, even though they try to distract me, I'm trying to help my students. They're still jerks. About it. So I have to do a F equals ma equation just for this 2 kilogram box. Okay, and you can do an F equals ma for the whole thing, like a whole system, or you can do an F equals ma just for a specific object. Either way, it'll work. Okay, so let's do F equals ma for this 2 kilogram box, because we want to know what's the force on this 2 kilogram box. So we'll call that force 2 kg. Well, now I just plug in. I know the mass. The mass is 2 kilograms. And I know the acceleration. The acceleration is the applied force divided by 9 kilograms. Pugs are good. I actually had a pug growing up. So 2 kilograms multiplied by the applied force over 9 kilograms equals 2 kg applied force over 9 kg. The units here are going to cancel out. So the force acting on this box, the 2 kilogram box, is 2/9 of the applied force. Like, look, it's always the ratio of that mass that I'm talking about divided by the total mass. That's always the ratio. The ratio of the forces, the net force being applied to the force acting on that individual box, always ends up being the mass ratio. Okay? You'll always be able to get it. 0.2222222, by the way. Thank you, Molo. Molo is a walking computer. You just ask him anything. All right, let's do another one. Once again, I'm like literally looking at the exam right now as I pick some out. Literally looking at the exam. All right, let's do you guys want to do another incline one or something different? Let me see. Let's do something different here. Let's do one like this. Move my... This is still an incline problem. They're all incline problems, let's be real. All of them involve angles. I like decimals. I mean, just round it to a decent amount. All right, let's say we have an object here. And it's on a surface, so no friction. It's on an icy surface. So no friction. And let's say it's a block of ice and there's 2 penguins fighting over it. Okay, there's 2 penguins fighting over this box. So we got one penguin. He's pulling this way on the box with the force of he's a strong penguin. So let's say he's got 4, 3, 5. I'm just making up numbers. I don't know why this is so hard. Let's say he's pulling on the box with 435 newtons. He's a swole penguin. He's doing great. And then we have another penguin. He's a little bit taller. So he's going to be pulling on this box at an angle with a force of 138 newtons. And let's say the angle here to the horizontal is very tall. Let's say it's 45 degrees. 45 degrees. So what we have to realize here, if we're trying to find, well, what's going to be the acceleration? Okay. What's the acceleration of this block here? Oh, and let's give it a mass. Let's say it has a mass of... It's a really heavy block of ice. Let's say it's got a mass of 20 kilograms. And we want to know the acceleration of this block. Well, once again, we should understand that F equals ma. We divide both sides by m. A is equal to F over m. So we need to get the net force acting on this box. That's an F, by the way. That's a very, very poorly drawn F. We need to get the net force acting on this box. Well, if we're worried about its motion horizontally, then we're only going to care about the parallel forces. So we got to break apart this 138 Newton force here into 2 parts. And the only part we really care about for this problem, is the parallel part. Okay. Part parallel to the ground. So if this is my angle, then I can use cosine to find this force because this is my adjacent side of the triangle. So in order to find that force, I'm going to do 138, my hypotenuse, times cosine of 45 degrees. Okay? 138 times 45 cosine. And I get, and Han Molo, you can check my math. I get 97.6 newtons. So already this is wildly inaccurately drawn, because this force is 435 and that's 976. So this arrow technically should be like, this penguin is so swole, so angry. That arrow should actually be like that big. Whatever, I'm making up numbers on the fly, chat. Give me a break. So the net force here is going to be the sum of these two forces. Now, if they're opposing each other, which they are, I'm going to subtract those forces. So 435 newtons minus 97.6 newtons. So I get a net force value, 435 minus 97.6, of 337.4 newtons. Okay. Now I just have to plug that back into my acceleration equation, because I know that the net force is also equal to mass times acceleration. So if I just divide both sides by mass, I get the net force, 337.4 newtons, divided by the mass of the object, will tell me my acceleration. So let's divide that out. I get an acceleration of 16. I am not rounding to significant digits here. Of 16.87 meters per second squared. Okay. And once again, if you guys have questions, ask, right? You could ask in chat. It seems good. Molo's trying to do the math in his head currently. It's very impressive. Very impressive. If you guys have questions, make sure that you either, I got my phone, so you can message me and remind. And I think I have a bunch. No, that's all pointless Discord stuff. Okay, good. Or you can message me in, or message the chat. Okay. Let's take a look at another one. Let's do like one or two more, and then we'll call it a night, because it's 8 o'clock. And you guys have more studying to do. All right, how about a question like this? You have to know kind of the unit circle, Bad Pug. That's actually a good question. You have to know the unit circle. Oh, do you know what we should do? Let's do some of the Khan Academy stuff. Let's do the Khan Academy stuff. Let's do some of those practices together real quick, because some of those you will see very similar questions to that on the test. So third law is pretty basic, just understanding reaction pairs. But it's still good to go over real quick. So let's just do a few of these, and then I'll do some of the angled ones. Sine little angle equals little angle. Otherwise, yeah, unit circle. Yeah, that's true. So what is the equal and opposite force for the force of a horse pulling forward on the wagon as described by Newton's third law? So if the horse is pulling on the wagon pulling on the horse in the opposite direction would be the reaction. So the action-reaction has to happen between the same pair of objects. So if the horse does an action on the wagon, the reaction would have to be the wagon doing a force back onto the horse. Okay, what is the equal opposite force for the force of the boy pulling on the bone as described as Newton's third law? So if a boy and a dog are both pulling oppositely on the same bone, when they pull as hard as he can, well, if the boy's pulling on the bone, then the bone is pulling on the boy. It's not the dog doing the pulling, technically. Or it's doing the pulling, but he's not doing the reaction. It's the bone doing the reaction, because the action and reaction have to happen between the same pair of objects. All right, person rides an elevator. What is the equal and opposite force for the force of the elevator pushing up on the person? Ooh, that reminds me. We should do an elevator problem together, actually. We should do an elevator problem real quick before we end the stream, because you will see something like that. What is the equal and opposite force for the force of the elevator floor pushing up on the person as described by Newton's third law? So if the elevator floor is pushing up on the person, then the person's pushing back down on the elevator floor. All right, let's do an elevator calculation question real quick, because you will see one of those. Okay. Person in an elevator. So a person standing on a scale and inside of an elevator. So let's say the blue thing is the scale. I got a person chilling on here. Okay. So what your weight is on a scale is technically the normal force. Okay, so the normal force we can find based on the net force equation for this object, right? So this person has two major forces acting on them when they're at rest. Okay, they have the normal force going up, and they have the weight going down. Now, if the object's accelerating, those two forces are not going to be the same, not necessarily at least. So if we know that the net force of an object is equal to its mass times its acceleration, and we know that the two forces acting on this person are the weight pulling down and the normal force pushing up. And once again, whether you subtract or add here, I guess depends on whether you think up or down is the positive or negative. So if we want to find the normal force, we can add it to both sides and then subtract ma from both sides. So we get the normal force is equal to mass times the acceleration due to gravity minus mass times acceleration. Okay? So the only difficult part here is knowing the mass and then knowing whether you're going to add or subtract the acceleration. Okay? If the elevator is accelerating upwards, okay, so if the elevator is accelerating upwards, remember the person's going to feel heavier because they're going to feel like they're being driven down into the elevator. If the acceleration of the elevator is downwards, the person's going to feel lighter. Okay, not a lighter. That's acceleration. Lighter. Because it's like the floor is dropping out from underneath them. Okay. So when the acceleration is downward, subtract. When the acceleration is upward, add. Okay. That's basically how you're going to do it. A lighter. This is lighter. Lighter. All right, so let's do a problem. Let's say the elevator is accelerating upwards at 5 meters per second squared. Okay, well, that's the acceleration, right? And let's say this person is a 50 kilogram person, and we want to know what the scale is going to read, what their new weight's going to be. Well, it's pretty straightforward. 50 times 10, what I get here, all right, the acceleration due to gravity is 10, minus 50 times 5. But this would be plus, I'm sorry. Because if we're going upwards at 5 meters per second squared, then I'm going to add, because it's going to cause my weight to go up. So 50 times 10 is 500. 50 times 5 is 250. So the person would feel, instead of being 500 newtons, they would feel like they're 750 newtons. Now, if the elevator is accelerating downwards, let's say it's accelerating downwards at 3 meters per second squared, we can do the same thing, but this time we're going to subtract ma instead of add ma. So once again, we added ma here because it was going up, and we should understand conceptually that's going to make us feel heavier. So the scale this time is going to read the 50 times 10, or 500 newtons, the weight of the person, minus mass times acceleration. I should be writing in my units. I'm a bad person for not writing my units. So that's going to be 500 newtons minus 50 times 3 is 150 newtons. And that's going to be, what, 350 newtons. So they're going to feel lighter. Instead of feeling like 500 newtons, they're going to feel like 350 newtons. Okay? So know how to do those problems. Those are pretty simple. It's just understanding that the net force is equal to the weight minus normal force. You have to rearrange to solve for normal force because that's what the scale is telling you. It's accelerating upwards, you add. Accelerating downwards, subtract. Okay? Should be pretty easy. All right, let's run through one set of Khan Academy problems. Let's do the angled ones. Maybe 2 sets, we'll see. Or we could do a unit test. Let's do an angled force one. All right, so a box of mass M is pulled at an angle theta by a force Fp along a frictionless surface. The box accelerates to the right. What is the magnitude of the normal force? Okay, let's draw this out because it'll help us. And I recommend drawing out these free body diagrams tomorrow when you're doing this because it's going to be useful. If you could reason your way through it without, that's fine. Okay, but generally you're going to want to draw these out. So let's go back to our notebook real quick. And let's draw a free body diagram for this object. So for this object, we have the applied force, they called it FP. And we should understand that we also have a weight pulling down. So mg. And we have a normal force pushing up. Okay. If this is at some sort of angle, theta, we can split up this. Did I write FG there? That's supposed to say FP. FP. My bad. We could split up this angled force into two parts, right? So we could split it up into a horizontal component. We'll call that FPX. And we can split it up into a vertical component. Call that FPY. Since FPY is facing that angle, we can find it by taking our hypotenuse, FP, and multiplying it by sine of theta. Once again, this is facing the angle, so it's opposite. All right, we don't really need to worry about the horizontal in this one because it's asking about the normal force. So I'm not going to bother doing that, but if you wanted to, it would just be FP cosine theta. All right, now this object is not accelerating up or down. So when we do the net force equals the sum of the forces, well, the net force is 0, right? It's not accelerating. So 0 newtons should be equal to the sum of these forces. Well, the force pulling down is mg, and that's going to be subtracted by Fn minus Fp. So if Fp, I'm sorry, sine theta. I almost screwed that up. Fp sine theta. The vertical component, right? These two are going to add together to oppose this down here. Okay, these two are going to add together to oppose this down here. So if I wanted to find the normal force, just add Fp sine theta and subtract by mg, right? This is 0 newtons. It's not on, 0 newtons. Add Fp sine theta, subtract mg, and that would get me Fn. So I'm looking for Fp sine theta minus mg. Let's see if we can see that. And we see a similar answer right here. Sweet. Got it right. All right, box of mass m is pushed at an angle by force Fp along friction of the surface. The box travels to the right with acceleration a. What is the mass of the box? Okay, so we know it's accelerating, and we know it doesn't have any friction. So we should be able to figure this one out as well. Let's go back to the notebook. Okay. So we got our box. M. Was it being pushed downwards? Let me check that again. Yeah, it's being pushed downwards at an angle. So instead of, I don't like having it up here. Even though it's being pushed downwards up here, I'm going to start the vector like this. It's the same thing. It means the same thing. And we know it has some sort of acceleration to the right. So it does have an acceleration going this way. So it's accelerating. And we know there's no friction. We know there's no friction forces. Also, where was that angle? Let me look at that one more time. All right, so the angle is in the bottom left corner, so I'm just going to draw it right here. This is Fp, and we want to know the mass. Well, the only force acting horizontally on this object is the horizontal component. I drew this totally wrong. Forget this. I'm just going to draw it like how they had it, so I don't make stupid mistakes. I'm just going to keep it up here. I'm sorry, I was getting too fancy. All right, so the only force really that we need to know about acting on this object is this horizontal component right here. Okay, is this horizontal component right here. So if this is Fp, then this horizontal force is adjacent. So I can find this by doing Fp cosine theta. And that's the only force, because there's no friction, that's the only force acting horizontally on this box. So that is my net force. I'm guessing that gravity is going to balance out the vertical part of this and the normal force because it's not accelerating up or down at all. So the only net force acting in the direction of the acceleration is the horizontal component of Fp. Well, I also know the net force acting on an object is equal to the mass times the acceleration. And the net force is this, Fp cos theta, the horizontal component of that applied force. Now, if I'm asked to find the mass, divide both sides by the acceleration. Mass is equal to Fp cosine theta divided by A. And we will see if we have a right answer, or if we're going to embarrass ourselves on stream in front of 40 people. Fp cos theta over A looks good to me. Yay, we got it. I'm sorry for that. Ugh. Sorry for the coughing. Give me a second. Parched. All right. Box of mass M is pulled at an angle theta by a force Fp along a frictionless surface. The box travels to the right. This is basically the exact same question. And then a box of mass M is pushed to an angle by a force Fp along a frictionless surface. Was the magnitude of the horizontal acceleration. Okay, this is basically the same problem as the last one. I can do this one real quick, actually. I'll try to stop dying, no promises. I appreciate your concern. So this time they asked me for the acceleration, not the mass. It's the same. We can start from here again. It's the same idea. If I'm trying to get the acceleration, I just divide both sides by the mass. The acceleration is Fp cosine theta divided by m. Same idea. Right there. All right, sweet. All right, so anything else? Anything else you guys have questions on? Want me to go over? We'll look at the test one more time. Oh, we already looked at that. Did that one. Trying to think what else. We went over Atwood machines. We went over the forces and angles. Oh, we could do a hanging mass one real quick. We went over. You guys know, hopefully you know how to draw free body diagrams by now. All right, what about an object accelerating down an incline? We could do one of those calculation problems. We could do one last one like that if you guys want to. I don't really care. No, Golden Wedgie, I'm sorry. Sorry, we cannot. Don't get circuits. That's second semester. You're spoiling it. You're spoiling it. All right, let's do one more. And we'll do another incline problem. This time the object's accelerating down the incline. Well, hey man, there's lots of resources on the internet if you actually want to learn more about circuits. There's lots of resources. This is the worst inclined plane I think I've ever drawn in my life. Like a bad wedge of pizza. It's too late, Pokénop. Too late. The time has come. Come and gone. All right, so let's say we got an angle here of, I don't know, 15 degrees. Okay. We got a mass here of 10 kilograms. And it's accelerating down this incline at a rate of 4 meters per second squared. Okay. So let's say we want to know about the amount of friction. How about that? It's got some friction, and we want to know the amount of friction acting on this box. Actually, acceleration of 4. Whatever. It's fine. We'll get the amount of friction acting on this box if it is accelerating this way. Hopefully this problem is physically possible because I'm just making up problems as I go along based on what I've seen on the exam. So hopefully this physically is possible. I guess it just depends on what the coefficient of friction here would be. But whatever. Let's go through this. So the first thing we're going to figure out is what's the net force acting on the box. Well, the net force acting on the box is basically mass times acceleration. Well, there's no need to overthink this. If the mass is 10 kilograms and it's accelerating at a rate of 4 meters per second squared, once again, I do not promise these numbers will work out in the end because I'm just making them up off the top of my head. The net force acting on this box is 40 newtons. Okay, mass times the acceleration. Okay, so we know the net force is 40 newtons. Next thing we should probably do is draw the free body diagram. So we got weight pulling down. And the weight, we already basically know what that is, right? It's mass times the acceleration due to gravity. So mass times the acceleration due to gravity here would be 10 times 10, or 100 newtons. That gravity we could split up into two parts. Perpendicular part of gravity and the parallel part of gravity. The perpendicular part of gravity we can find by doing mg cosine, because our angle's right here, 15 degrees. You do mg cosine theta, and in this example that would be 100 newtons times cosine of 15 degrees. I already don't think these numbers are going to work out, but the math will work out, so that's the important thing. And I get a parallel force of gravity. Actually, it might work out. I get a parallel force. I'm sorry. This is perpendicular. What am I doing? What am I doing? That's perpendicular. The perpendicular part of gravity, so the part that opposes the normal force, perpendicular, is 96.6 newtons. Yeah, I could already tell this math isn't going to work out, but it's fine. The parallel part is mg sine theta, because that's opposite of the angle. And that's going to be the 100 newtons times sine of 15 degrees. It's going to be a small number. That's 25.9 newtons, if I did my math right. Okay, let's think about the other forces acting on this box. You have the normal force pushing up. That normal force must be equal to the perpendicular force of gravity, because once again, this object is not accelerating upwards into the air. It's not accelerating downwards into the ramp. So it'll also be equal to mg cos theta, which is 96.6 newtons. They're going to have some sort of frictional force opposing the motion here. I'll call that F sub F. And that's basically it. Now, technically, I could calculate F sub F based on the numbers I gave you, but the math I don't think is going to work out 100% perfectly because I'm just making up numbers as I go along just to show you the algebra. So it'll have to be good enough. It'll have to be good enough. I don't know how to respond to some of those things in chat right now, so I'm just going to ignore them. Okay. So basically, what we can do now is we can figure out the acceleration of... No, wait, we already know the acceleration. We can figure out the frictional force by figuring out what the acceleration is, comparing it to the parallel component of gravity being subtracted by the frictional force. And once again, the numbers aren't really going to work out here super well, but the math will still make sense. So the net force of the object, so m times a, is going to be equal to the parallel component of gravity minus the friction force. Once again, the parallel component of gravity can be found by doing mg sine theta minus the frictional force. So if I wanted to get that frictional force by itself, I could add F to that side, subtract ma, and friction would be equal to mg sine theta minus ma. Now I can just plug in from there. Okay. So I could go from there. I mean, technically, you could also find friction by doing the coefficient of friction times the normal force, and then just dividing the force of friction by the normal force. Actually, we still could do that. Let's do that real quick. So mg sine theta, 25.9 minus 40 gives us a frictional force that is too big, but that's okay, of about 14.1 newtons. And then if I actually wanted to find the coefficient of friction, I know the force of friction is equal to the coefficient of friction times the normal force. Divide the normal force from both sides, and I get the coefficient of friction equals the force of friction divided by the normal force. So in this case, it would be 14.1 newtons divided by the normal force of 96.6 newtons. And that should be equal to about 0.146. And remember that coefficient of friction does not have any units. It's just a ratio. Okay, just a ratio. All right. Any other... Rage, I'm sorry to hear that, dude. I hope you feel better. Any other specific questions? All right, I got my phone ready for remind questions. I got chat open up. Okay, so this is a good question. I got a question that said, ask, will we be given equations? Okay, will we be given equations? Good question. I will say this with regards to the equations. You only need 2 equations, okay? You only need 2 equations. Here's the 2 equations that you need. Let me move this real quick. Here's the 2 equations that you need. The net force equals mass times acceleration. The force of friction equals the coefficient of friction times the normal force. And then that's it. I mean, all other equations are derived from those 2. And just know that MA is the sum of forces. We could set MA always equal to the sum of the forces acting on the objects. Okay? That's all you need. And then you just need to know your trig, right? So if you got a right triangle and you have a certain angle, right? Just know that this side is opposite. This side's adjacent. That's the hypotenuse. Adjacent can be found by doing hypotenuse cosine theta. Opposite can be found doing hypotenuse sine theta. I mean, know how to do those. How many questions are on the test? I refuse to answer that. The worst question. How many questions are on the test? Enough. Enough questions. Enough questions to fully assess your knowledge on said test. So F equals MA. And force of friction equals... I can't even... My phone's trying to autocorrect right now. It's very annoying. Very annoying. All right, any other questions? Or I'm going to call it a night. Any other questions? I left for 10 minutes. Are we still here? Number 3. Are you asking 3 questions? Are you guys trying to guess the amount of questions on the test right now? Or do you actually have a legit question? When you say number 1, I don't know what that means. There's more than 1 question. There's more than 3 questions. Around 20 is close. It's around 20. I turned off alerts, Rage. I turned off alerts, but thank you nonetheless. All right, I'm ending the stream. I'm going to end it there. Hopefully you guys found this helpful, okay? I'm open to doing stuff like this in the future, especially before quizzes, exams, things like that, if you guys find it helpful. No penguins on the test. Yes, Pocono. Yes. Okay. Everyone have a great night. Study. Okay, I'll be on remind. Not Red Dead right now. No. I'm not playing video games right now. I'll be on remind. Let me know if you need help. Okay? Rage Factory, you better study. No watching me stream. You guys got to study. All right. Good night, everybody. Have a good one.